Okay, as you see, I'm going to record the lecture. Just in the case, I try to upload the recorded video also on the Google Drive so you can find the video. But I don't know because last time I tried to record the video by this Mac computer. So the volume of the file exceed more than half giga. So let's just see that how much will be the volume, the size of the file. So anyway, I will record that, and after first lecture, let's to see that I can upload them or not. Let's go. So the textbook I send you is the textbook of Ryan and Norton. So it's a nice book, Stellar Evolution, Nucleosynthesis, and almost a new, because astrophysics since 2010 doesn't change very much. Just even at the level of technology, it doesn't change. Of course, you know about history of the space race and the astrophysical project. So it was started in 1960. It was a competition between the Soviet Union and United States, and the Soviet Union was the first country who sent the satellite Sputnik to the space, and then United States and the Apollo, and then this competition continued. But recently, as you know, other country entered. So this history is because I want to tell you that after 2010, nothing changed very much. I will tell you. So now we have the project, the space project from China. We have space project mainly from the European Union, and we have a space project somehow from the India. So this is a very active, and also Japanese scientists are actively working for the scientific project regarding the astrophysics, but mainly with observations. The Chinese has very good opportunity and instrument for detecting the neutrino, and there's other stuff. So in 2010 and so far, just 10 years, the things which changed was that the progress for the Mars project in the NASA, and also the NASA decided to give the project to the private sector. So there is now the private sector are sending they are trying to sending the man and back the man to the moon also in 2023, 2023, just in 3 years. But let's see what's going. There are some other books there here, but we use the textbook, and we will read the whole 8 chapter from textbook, and there is nothing more you needed to know. I will stick to the textbook, and I ask you also to only focus on the reading the textbook. The assessment component, it is a flag, is bouncing actually. There is a homework. I will give you the homework, maybe 3 or 4 set of the homeworks to do and submit it. There is a midterm exam in 30% and final exam 50%. And there is a SQ regulation to sit in the lecture. So let me know if you have an excuse for any lecture, because I have to make the attendance list and the portal. And I will sometime will ask you something that I want to know that you are alive or not, and you are listening and watching the speaker or not. The time of the lecture is a little bit tough. I know 80 minutes. We try as long as we finish the slide and there is nothing, so we will end the lecture. No hurry, no problems. And all of them, this information. So as I told you in the textbook, please let me know if you have any questions before I go to the next slide. I want to tell you about assessment components. So it is possible for somebody to do a project, but the project is not mandatory. I don't want to ask you, all of you, to do the project. If somebody wants to do the project, individual project, or if you want to do the project together and two persons, which will be harder than the single project, then you have to contact me and I will provide for you the information for the project. The course content, so there is an 8 chapter here. As you see, the main sequence star is the first chapter. We will talk about the categorization of the stars using the Hertzsprung-Russell diagram, as you remember. Remembering some concept about luminosity, about the temperature, and mainly we talked about the sun today in this lecture. And then we will talking about the stellar formation equation, how many equations you need to study the evolution and the creation of the stars, and what is the solution for this equation, how people solve those equations. And we will talk also about the nucleosynthesis, how this energy, this thermonuclear energy will be produced inside the star, mainly inside the sun, and what is the role of this thermal energy in comparison to gravity. What is the relation between gravitational energy and this thermonuclear energy. The second chapter and third chapter you will see, and you will end with chapter 8. We do our best to complete the whole chapter. Mainly each chapter takes, first chapter we took just 2 lectures, but the other chapters it took longer because of there are longer chapters. Sometimes we will stop 2 weeks in one chapter. So this is what we expect. Any questions about them? So then I will go to next one. If you don't ask the question, I will ask you because I wanted to know that are you here or not. Oh. So you have to tell me, because when you don't tell me that, how I know that the connection works perfectly or not? Because I talk a lot and okay, you have a question here about the test. No, we will do the test in the Google. So the test will be by submitting a Google form to you, or even if I will submit the question directly by email to you. Okay. So do you see my screen now? Yeah. Okay. Good. Let me know even if you are presenting to everyone. Click here to return to the video call. Okay. So is it okay? Still you see me? Okay. Okay. I have to make full screen the slide, otherwise I don't know that. So as soon as you didn't see my slide, please open the microphone and tell me the problem, okay? Because when I checking the slide, I don't see this Meet Google, okay? Well, all right. So we start by first chapter. So the main sequence start. The blue titles are the one which I will present today. The 4 remaining will be for next lecture. Among the rest, the only important one is the number 3. The other one are just the description. So number 3 has something like the equation and those stuff. Okay, what is the star, and you know how the star started, and what is the starting point? For example, the sun, how the sun started. You don't expect that, but any star formation started from a cloud of cold gas. How much cold are there? They are very cold, actually. They have a temperature between 10 to 20 degree Kelvin, and you know, even sometimes 0 Kelvin. So 0 Kelvin is problems. Do you know why 0 Kelvin? Just above absolute zero. We cannot go to the 0 degree of Kelvin temperature. Anybody know why? If you know, just turn on the microphone and tell me. The cold gas, actually, the cold gas with temperature of 10 up to 20 degree Kelvin, so is composed by the light atoms like hydrogen, helium, and sometimes inside these clouds there are some elements, heavy elements. Do you know what kind of the metals or elements could be existed inside this cloud of cold gas? Do you expect anything? Uh, hmm? Can you imagine what kind of the metal will be inside his clots? Okay, those are
Doctor,
different clots.
doctor,
Yes,
can you
yes,
repeat the question? Can you repeat the
yeah. I
question?
mean, yes, yes. I say when the star want to make formation, so there is some light elements like hydrogen and helium, and there are some heavy elements like they call it metals. So do you have any idea about what kind of the heavy elements are here at the beginning? Gold. Uh, you don't expect, but it's gold and iron, and those heavy elements are here. So that's the answer. Okay. So what is happening after that? This cold gas will collapse. So what does it mean, collapse? Collapse means that because of gravity, it will be contracted. You know? If it is spreaded like a particle in the space, so gravity make them more close to each other, close to each other, and this gravitational pressure try to keep everything close to each other. There is a gravity, and gravity is an attractive force. By gravity, everything wants to be close to the other one. So how you describe the gravity? So gravity is described by gravitational potential energy. So gravitational potential energy is responsible for trying to keep together the clothes and make them close and contract. You see my hand, so it means that the size of these clothes are large now, and then by gravity it reduces to this process called collapse. When this process of collapse continued, the things which happen is the gravitational potential is changing. Do you think the gravitational potential increase or decrease it when the collapse starts? What do you expect? Hmm? Do you have any idea? When two objects be more close to each other, the potential energy is.
I think it will increase, doctor.
Yes, sure, sure. Because the force will increase, huh? When they become very close, the force will be more stronger. So this is exactly what is happening here. Of course, we don't have two particles here. We are talking about the clouds of the gas particles. So it's a million, trillion, or Avogadro number, or whatever. Is actually basically it's infinite numbers. a very large number. So yes, the gravitational potential is very increasing, so increasing. So this gravitational potential energy actually is a type of the energy, and it will be transmitted, or it will be transferred, or change the shape to the heat energy or thermal energy. And when the gravitational potential changes to heat, then the things which happen, and this is not very clear here. Look, this is what I say here. The pointer, I needed the pointer. 1 minute, just how to activate the pointer here. Here's the pointer. Okay, maybe I will show. So this P and rho and T, actually they are just I increase the size here, because this is the first I size zoom. Okay. So when the gravitational potential change to heat, so the pressure, what kind of the pressure? This is a thermal pressure, and the energy density, this is energy in the per volume, and temperature will all increase. So when the temperature increases, what is happened? It's like a kitchen in the oven. So when the temperature increases, so it becomes glowing. It's glowing and it's firing. But firing in which sense? First, it started to be infrared. I mean, the energy, the thermal energy which emitted from this glowing, this bowel, or this hot bowel actually in your kitchen, had the wavelengths between 700 to 100 micrometer. So this is called infrared. And then these infrared wavelengths will reduce to 10 nano or to the 10 micro. And do you know that when the wave, or when the energy drop to such wavelengths, this is called optical wavelengths, the frequency will be increased. And what is going here is that the systems got some more energy, but this type of energy now is thermal energy. There is a very easy reason to understand that why the high temperature will make such energy. The thermal energy is, in physics holiday, the thermal energy, average of the energy of the particle in the box, for example, in chapter 19, is proportional to the temperature. So when the temperature increases, so the energy increases. But why frequency increase? Anybody know? We expect the temperature will increase it when the glowing started, but why the frequency will increase? What is the relation between energy and frequency? Because the frequency is very high here, 3000 terahertz or 300 gigahertz, so it's a very large number. Do you have any idea about
Maybe
why the
maybe
energy?
Because the energy is high.
No, temperature is high, but I mean, why the temperature is very high, why the frequency increase? Why? What you think about it?
because the kinetic energy of the atom will increase, and due to that the frequency will increase.
So
So
there is
temperature will increase, and
a
then
relation.
kinetic energy will increase.
So there is
And
a
then after,
relation.
yes,
There is a relation between temperature increasing and the frequency. This is the Planck equation. Actually, energy of the systems is proportional to the frequency. When the frequency increase, the energy increase, and when the energy increase by temperature, same time the frequency will increase. But this is a very high frequency. 3000 terahertz is very high. And how much this temperature will increase? You need this thermal energy to increase the temperature up to the million Kelvin. A million Kelvin is the starting temperature to make a star. The stars are started from the cold. They actually are burn in the cold place, but then they with the cold clots, but then you need a million degree Kelvin to start the real star formations. Nuclear reactions will start at this temperature needed to start the nuclear reactions. So when these clouds after the collapse reach this high temperature, the thermonuclear reaction will start, and these thermonuclear reactions will affect the gravitational collapse. It started to fight with the gravitational collapse and make a non-gravitational source for the energy. Before of that, only was gravity. It will increase up to the level that the pressure of thermal increased or greater than the pressure of gravitational collapse. So when the thermal energy reaches such level of the pressure, so the balance will be break in the favor of thermonuclear reactions. And finally, the things which happen is that the star burn. So the star is the first moment of the one baby star actually. When the thermal pressure greater than the pressure of gravity, then the phase transition happens from cloud to star. And after that, you call these clouds as a star. By definition, a star is an object. It is important that the star is an object which nuclear reactions are sufficient to balance the surface radiation loss. So here there is a short, I want to just watch this too. This is what you see that, these simple diagrams actually gives you a possibility to the balance between the gravity and the pressure, thermal pressures. You see that. When the gravity decreases, so thermal pressure increases, and that makes always the balance. Okay? Great. Okay, you still see my slide? Because when it is okay, you see? Okay, good. What is the Hertzsprung-Russell diagram? This is what you read it before in physics. Read before in physics in the mysteries of universe. So Hertzsprung-Russell diagram gives you a diagram to compare the star and make categorize the star. So stars are categorized in this diagram based on their luminosity. Luminosity you will see, and you may remember it was related to the power which emitted from the star. And it is a relation between luminosity and effective temperature. So basically it gives you a map of all the stars. They are they are set in the different islands. So you have an island of white dwarf, you have an island of red giant, and you have a narrow of the stars, which we call it main sequence. And as you remember, the sun was in the main sequence category. So there is a two type of Hertzsprung-Russell diagrams. So first Hertzsprung-Russell diagrams is the one which observational one, and in the observational one, instead of the luminosity, you have absolute visual magnitude. It's called MV. There is a relation between MV and L, but we don't want to talk about that. And this is a vertical axis, and stellar spectra type on the horizontal axis. So in the original observational diagrams, there is not such temperature there. What is the problem to, what is the difficulty to put the temperature as one of the axes in Hertzsprung-Russell diagram? The problem is that, as I mentioned here, like underline, the problem is that, sorry, no, okay. The problem is that the problem is that the temperature cannot measure for the stars. We are not sitting in the surface, and there is no surface. I will explain you in the next slide that talking about the surface is very odd. So stars doesn't have any surface. I mean the sun, for example. Huh? There is just some region we just call this surface, but it's not actually a place which you can move, or like what you are moving on the Earth. So it's a completely different things. So you understood that temperature cannot be easily right for the stars. We don't know temperature of many stars, but what we know is that the spectral lines, the line of the emitted, the color of the emitted light which came from the star to us. So that color of the light which come from the stars, they are a good evidence for us to categorize and to understand the temperature of the black holes. So after all, we have a Hertzsprung-Russell diagrams, and if you combine the theoretical aspects like a data analysis and using the observational fact, then you can have a real Hertzsprung-Russell diagram when the vertical axis is luminosity, and which is, what is luminosity? I will explain next slide. Is energy radiated per unit time, and the horizontal axis is temperature, effective temperature. So what temperature you can use for this? What is the type of the temperature for the stars? Star doesn't have an opaque solid surface, so they don't have a surface, as I told you, and the light which came from a star actually comes from different layers, and each layer has a different temperature. Yes, as you remember in the 3901, for example, for the sun, there is a core, and after that, the different layers, radiation zone, and whatever. The one which, the light which came from the core is very, very high temperature than the light which came from the emitted radiative zone. So when you have a different layer, so you have a different temperature. So how you can define the temperature for the star if you have several levels and different temperature? The key idea is using the idea of black body. Black body radiations is one of the interesting experiments in the physics. If you make this room dark, and if you just make hot a rod, or a metal rod, then you will see a different color from that when the temperature of this rod, for example, if this is a metal rod, for example, if the temperature of that increase, this is what you can do at home also. So you see that the color will change, and it depends to the element. Sometimes the color which you see in the darkness from the fire has a blue or red or whatever different colors. So this is because of different elements like sodium, like iron, and those other. So black body radiations, the radiation which we observe it from the hot object, is a way to understand the luminosity of the star. Luminosity, which we will explain that this is a flux, or this is the radiant flux of energy per area, per unit area, is related to this is a L. The luminosity is related to the temperature, as you see. But this is a Stefan Boltzmann law. So the luminosity is just 4 pi r square. This is the area of the star. R is the radius, for example. Sigma is a constant, which called Stefan Boltzmann constant, is a very tiny number, 5.6, 10 power minus 8 watt per meter square Kelvin 4. And T is effective T is the temperature which we label to the star. So remember that if you talk about temperature of a star, we mean the effective temperature. But what is the, from where this equation come? As I mentioned, this equation come from Stefan Boltzmann law. Stefan Boltzmann law make a connection between gradient flux F, which is the radiant energy per square meter and per second. So it's like a power per meter square, and the temperature of black body. So I want to show you, and then using this flux, which is the energy, as I mentioned, radiant energy per square meter of the surface area per second, you can define the luminosity. So just let me the spectral lines of the any star. By looking at the colors, you remember the colors in the physics 3901, spectral, atomic spectral. Looking at the color, I can tell you the temperature. Okay, let's watch a 3 minutes video about this Stefan Boltzmann. He's cool, so you just. Okay, I hope you like this break actually. So I know that when they are talking, sometimes they are fast talking or sometimes they are boring. So I'm trying to find the best video always. Anyway, let's back to the slide. If you see my slide still. Okay. Okay, but what is how you can use the black body radiation for the stars and what we mean by this surface? You see, you see much, all the information in that video of 3 minutes actually. You know, different layer has a different temperature, but we are referring to region which is called, which has a thickness of 500 kilometers. This is a photosphere and is the best definitions we have a surface for the star. And when we talk about the star in this chapter, we mainly talk about the main sequence. So main sequence of star, the best one is sun, because sun is the massive one, the most massive one, and also the physics of the nucleus process inside the sun is similar to the many other stars. Okay. So what you understand is that black body radiation can be used also for the stars because they observe any light which falling on them, so they actually looks like an object which you're hitting that object. Luminosity actually is a factor which, as you see in the video, which show you which object is more brighter than the other one. As I told you, stars has a different layer. So what information we have about the temperature of the different layers? What information we have? The information which we have is that the temperature for layer inside the star are much, much, much higher than the temperature of effective. What is the T effective? It is the temperature of photosphere. And photosphere thickness is around 500 kilometers. And if you go while the shallower layers has the lower temperature than the effective temperature. So the effective temperature is used to characterize the outer layers, and even if you're not able to define a really solid surface for this, so like a sun doesn't have a solid surface. It is a burning surface, It is a burning surface of the very, very hot gas, actually. This is the Hertzsprung-Russell diagrams. So, because I want just to show the Hertzsprung-Russell diagrams, just make it little bit giant. So, this is familiar for you from the previous course. So you remember this is the right side, the horizontal axis is effective temperature in the Kelvin units, and the vertical axis is luminosity versus the luminosity scaled by the luminosity of the sun. This L subscript dot, so that means the luminosity of the sun. So if the luminosity of the sun is 1, you see there are some stars here which they have a high luminosity, like here even in main sequence, but they should have also high temperature, as you see, and some is somewhere here, the sun. And we studied that in the 3901, so I don't want to talk about that. That was so. Basically, Hertzsprung-Russell diagrams gives you a map of the stars. What kind of stars? The main sequence, white dwarf, and red giant. So, and you know, may you remember from 3901 that the star finally will turns to the red giants. and sometimes in terms of the white dwarf, it depends to their mass actually. Those are this is the graveyard in somehow of the stars. And this is the intermediate place when the stars die. Sun is very important for us, so let's review the information for the sun. So the physical properties of the sun. So the mass of the sun is 1.9 10 power 30 kilogram. The radius of the sun is, as you see, 100 million or 100,000 kilometers. Luminosity of the sun is 3.8 10 power 26, so it's very, very huge numbers. So just compare that with the power of your car, for example, horsepower, and just read the information that compare with luminosity of the sun. Effective surface temperature is around 6,000 Kelvin, 5,780 Kelvin. And it's very interesting that when the volcano happen in the earth, so actually at the earth, sometimes this temperature will increase up to the temperature of the sun. All right, so the age of the sun is 4 billion actually, 4 billion. So, and the age of universe is around 14 billion, 13.7 to up to 8 billion. So 10 billion after the creation of the universe, according to the Big Bang theory, the sun was born. Sun is young in comparison to the universe, It's just 4.5 and this is a 14, so around 1 or 3 or 30% of this universe is very old actually. The density of the sun is very high. And do you know the density of the earth? We are talking about the sun. Who know what is the density of the other planets? If you know, just write me. Don't make it the Google, just tell me that approximately. All right, you are away. Some of you are away, or anyway. The temperature of the sun is 15.6 core temperature. So the surface temperature, photosphere temperature, 6,000, and this is a million. This million, you remember, was the temperature with a minimum temperature when the star want to start to burn. And core pressure is very high, 10 power 16 Pascal, so it's very high temperature. But how we estimate the potential energy, and how we estimate the gravitational energy? You know, to estimate the potential energy, to estimate the potential energy of any star, we need tools. So the tools which we use is a Virial theorem. So this is a theorem from thermodynamics. Virial theorem is talking about the average of the pressure of the molecules inside a gas. Virial theorem say that the volume, the volume average pressure. I mean, if you make the average of pressure over the volume, in the equilibrium state, is given by the equation 1.2. So if you give me the gravitational energy, and if I have the volume, so then I can find this Virial theorem. I will ask you to, and the homework I will ask you to go and write for me why the Virial theorem is like that. So this is will be the open for you to go and find the derivation of that. So gravitational energy is very hard to compute it. So if you want to know how to calculate the gravitational potential energy for this sphere, you need to know the information about the density. So even if you consider the density of a star uniform, even with this situation is very complicated. Anybody know how to calculate the gravitational potential energy of a uniform star? Hmm? Gauss theorem, huh? If you go to the physics 2, there is a Gauss theorem there. Gauss theorem say that if you have electric charge, then you can find electric field for very symmetric distribution of the charge using the simple integral. Gauss theorem can be used also in the gravitational physics. If you have, instead of having a distribution of charge, if you have a distribution of the mass, then also you can calculate the potential energy using the Gauss theorem. But to calculate the potential energy, you need to know how much is the gravitational field magnitude as the distance r. So if this is a star, so you have inside and outside. Inside of that, you have a mass, and consider the mass uniform distribution. I mean, just consider the masses with this uniform density, whatever you want, some numbers. Then you have outside of that, there is no mass. In outside, you just see the whole sphere. So the gravitational field inside and outside will be different. Tell me that if you think about the r like a distance from the origin to any point, what is the proportionality of the gravitational field with respect to the r for inside and outside? If I am standing outside, the easy one, how gravitational field changed by r? It is linear, it is r square, it is inverse r, it is inverse square r, it is root r. How it change? Do you know? So let's, for example, you are standing outside. So the gravitational field for outside, I show by this, will be minus g. M is the mass of this star over r square. So this is the gravitational field for outside. Okay, I can write here out. Okay, then for inside, it is not very easy, but I will give you that like a homework later. But you can go and find for me that the inside will be like that for inside. Okay, r is the radius of this, and then you have g for inside and outside. So let's to plot, huh? Let's plot. So I want to plot, for example, just to see. Okay, plot. The outside is 1 over, inside is proportional to r. You see, it is proportional to r inside, and outside is 1 over r square, huh? Okay, and the range which I want to consider is the whole range, 0, for example, to 10, for example. Okay, this is when you are inside. So this is the region, for example, the region which they 10 is very high. Let's do 5 on 2. Okay, when you are inside the star, for example, the star radius is 1. Do you see this? You see? If you see, just tell me, write me yes. Or everybody is asleep, I don't know. Okay, good. Because Raya writes me always, so good. At least one person not sleepy like me. So 1 here is the radius of a star. Of course, this is not, it is just to see how it's going. So G is the gravitational field. Inside it is R square. And outside outside the star, the radius of a star is 1. Outside it will be 1 over R square. So this is the, forget about this region. Those regions are, so inside it will be linear, after will be 1 over R square. So using that, you can find the gravitational energy. I want to just write how it's going, To find the gravitational energy, as we mentioned here, you need the integrating over the mass. I have a mathematical here. If you don't have mathematical, don't worry. If you have any software, if you have a pen and pencil, you can do those calculations. I want to do by mathematical because just to see, you will see something different. Okay. Let's back to mathematical. So the potential energy is um, is the integral in integrate integrate of what? Of the G. G. What is the G? G in and G out. G in over what? G in is over R, and the radius is 1, for example. Or radius, we take R, R. This is one part, okay? Plus, you are now integrating from 0 to R, from here, for example, to here. If R is 1, if R is not 1, I put R just here, okay? Plus what? Plus again, integrate, just description what is written is of this out. What is the range of integral now? Can you tell me? So you integrated the gravitational field from 0 to the radius, and then I want to integrate after that. Can you tell me what is the range? You're out of the star, so your radius will start from 0 to what? 0 to whatever you want. Whatever you want is the infinity.
Infinity?
Yes,
Infinity.
exactly. Yes, I find the infinity from this. So then let's to see what is going here. Oh, it is very, we forget many things, but anyway, it is okay, because I think here, for example, really it should be like square, as I remember, and now is okay, because now let's to see. This doesn't change. Of course, the graph doesn't change. But let's to see what is going here. So will be something like that. Of course, it is just, maybe there is some coefficient here or whatever, you see. Because I very little, I'm little worried about the units. It should be, let's to see. The Gauss theorem say that D is so R squared. Okay, because it should be written in density. But anyway, of course, this is not correct. But I want just to show you, because really not all the mass is inside the star. Yes, m is the total mass. So when you're sitting inside the star at the distance r, for example, when you're sitting here, not at here, I know that the mass here from here to here is m. But what is here if you are here? Because you are integrating. You are integrating over r, so you start integration from. So So the mass is not m, so it's something else. We can call it m prime. Anyway, so then this will comes like that. And if you give me the relation between m prime and m, then I want to promise you that you will get this expression. You see, 1.2. Anyway, I told you that I will give this like homework, or even I will maybe solve this problem for you like tutorial later. Just I want to show. And be familiar, this is a mathematical. So if you are a student, I think you can, this mathematical is, of course, is by payment, but there is a software which is called Maxima. You see this Maxima software? It's not very friendly, but do the same as the mathematical do, but it is open source, or whatever software you want. We don't need software very much, just I want to have fun, just show you something. Anyway, let's go. So this energy comes from those considerations, is integral and those stuff. Let's back to the slides. Okay, so virial theorem gives you the average pressure over the volume, respect, and the relation to the gravitational energy. So, for example, use the sun as a sample, so you can replace it, the volume of the sun here. You have the radius of the sun. Approximately, you know how much kilometer is the sun radius. Then you can have volume. So, and you have the gravitational energy, as I showed you in the previous slide. Then if you combine, you get the equation. This equation came from virial theorem, give you average pressure inside the sun. Few slides remain, and then we go. If you want to calculate, just set the numbers, just set the mass of the star and the radius of the sun. Radius of the sun came from this table, if you remember, and that gives you a lot pressure. But still this pressure is for the surface of the sun. Is much smaller than this pressure inside the core. Okay. And the density of the sun, the mean, then also there is a version of the virial theorem to find the average density. So average density means just divide the mass by the volume. So you get the equation 1.6 here. It is the same as the equation in textbook. If you set the numbers, you get a ton. The density of the sun is ton, actually. But it is not even heavy. It is just 1% of the density of the core inside the sun. Okay, this slide, I don't want to go through that. It's a little chemistry. This slide explains to you that how you can calculate this mass using the molecule mass. So just I want to say you that in the astrophysics, we use a concept which call it mean molecule mass. So this is a mean molecule mass. So because the star is composed by different elements has a different number of electron, proton, and whatever you see. And all the masses, we don't write them in the kilogram, of course. We use them atomic units. So the atomic mass unit is 1/12 or 12 times smaller than the mass of carbon. This is from chemistry, you know. So in the astrophysics, if we want to do calculation with the mass, usually we use the mean molecule mass. This is the symbol is mu. It's just simply is the like average of the number of particles which any type, for example, electron, positron, and proton, neutron, any type of them, multiply to the mass of each one in atomic unit over the total number. This is like average. You have some, it is like the making the average of the weight of the people in the classroom, not in kilogram, in gram, for example. Then each person has a 10 kilogram. For example, 70 kilogram is the weight of one person. 70 kilogram divided by the 1 kilogram is 1,000 gram, yes. divided by that will be get a number like atomic mass unit. Here you can call this body mass unit instead of the atom for the person. Then how many people like 70 kilogram you have? Right here, 1, 2, 3, any. Then go to the next person, 50 kilogram, 54 kilogram, 65, and whatever. And how many number of them has included? Yeah, and divide by total number. It gives you a number. Do you know what is interesting about this? Mean molecule mass always will be a tiny number. For example, it will be maximum for most star. For most of the star in the main sequence, this number is almost 2. And for many other stars, for example, is around 1 or 2. Look, for example, consider the mean molecular mass of the gas when it's just hydrogen. So hydrogen molecule is just 2H, which they connected with the atom with some atomic force together. So the mass of hydrogen molecular hydrogen is 2 because it is just 2 elements, electron and protons. And then uh, then if you have if you have anything which is like, for example, here they call it ionized hydrogen. If you have a different type of them, as I told you, I don't want to make this repeated and more confused for everybody. You have, for example, n number of protons. The mass of protons is MeP in kilogram. You know, is a big number. Divide by the atomic unit, atomic mass unit. It gives you some number. Then you have number of electrons here in your system. Divide, multiply to mass of electron in atomic unit. Divide by the total number of the proton and electrons. Then it's so funny is that the mass of electron in atomic units is almost 0 atomic electrons, and proton is reasonable proton. Then you get a number for the, for example, ionized hydrogen, you get 0.4. For any other chemical elements, you get a number almost 1 or 2 or something like that. These, anybody know why I say that this number, I say we have a problem with, I say that this number never exceeded 1 or 2. Do you know why? This is like probability, huh? It's like probability numbers, you know, probability is running between 0 to 1. You have here Ni, you have here Ni, and you have mass per atomic units mass. So this number is, you know, its maximum is, how much is that? Is tiny numbers, because you divide each mass to the mass of a carbon, and the number is the same. So this number never exceeded. It should not be 100 or something. It's almost is a tiny number. Anyway, we are going almost to the end. So, for example, there is example here. What is the mean molecule mass of neutral plasma when the atomic number is older 20, 30? For example, like the elements with 20. If you are, you know chemistry better than me, I remember, like, okay, the atoms with 20 or 30 electrons has the same protons. So if you again consider the number of the electrons, Z, for example, and this is the hydrogen, for example, this number of the hydrogen atoms is, for example, NZ, and this is the mass of hydrogen atomic unit, and this is the number of electrons, and this number of the electrons plus the protons, for example. So then this calculation gives you a function like 2z over z plus 1. And again, you see that even for not heavy elements, so because heavy elements, z is really large, as you know, in the Mendeleev table. But for elements like in the group of the cesium, for example, or something like that, when the z is around 20 or 30, so this mu again is around 2. So I want to tell you that the mean molecule mass never be large number. So this is one. Okay, this is a summary. Just I summarize, and then we end this lecture. So what we read it this today, I don't expect that the best today was the best, but we did our best actually. It will goes better smoothly. So we talk about Hesperon-Russell diagram. We say that this is a relation between luminosity and temperature, effective temperature. Then we talk about Stefan-Boltzmann, and this is a Stefan-Boltzmann law give you a possibility to estimate the effective temperature using the luminosity. Then we talk about how to define the pressure for the stars, so virial theorem. Then you needed to know that what is the potential, gravitational potential energy. I give you a simple calculation, how you, by integrating the gravitational field, you can find the gravitational potential energy. Then I talked a little about how to calculate the mean molecular mass. That's not important. And then I want to tell you that, like any other things, pressure can be averaged, and also you can define the mean density. And there is a relation between mean and density of the matter and the pressures and the temperature, but I didn't write that. This comes from the ideal gas law. PV and RT, you remember this relation, can be read it also in the virial theorem. Thank you very much. So I will stop it here. So now I will share this slide with you. So you will get the link to see the slide of today's lecture. So, and hopefully we goes to the next lecture again Wednesday. Okay, I will try. I will try to upload also the video, but let's to see. I don't know how much is the one time, because I preparing the experimental physics video for the student, and when I finished by this Apple computer, so the size was very huge. So then I did some software to reduce the size, and then the quality reduced. Anyway, I will try to upload that. So hopefully you will receive a link to the slides and also a link to the video. So thank you very much. See you. Bye bye. Yeah. No, Raya said that we study from no. Slide is taken from the book. Exactly. I just copy sometime from the book and put it in the slide. No, you have to read the book. If we finish all the chapter of the book, should not be very big also. This book is very short book. You have to read from the book, because this book, there is some exercise problems to solve. You have to read it from the book, but a slide will help you to summarize if you want to just summarize. Check on the book, okay? See you. Bye. Okay, see you.